Any of them? Hello, everyone. You can also show your face.
Yeah.
Purushottam is the TA. You have any questions, you can start typing and I will be happy to answer any of your questions. Yes, also.
The question will be there over there.
Yeah. But you will also be there in the chat. You can also sit on the picture. So how many weeks have gone over so far? And what are the topics which is completed?
So, like, the current week is the 8th week of the content.
Okay,
So,
what is the content?
So this week is the 8th week's content is the harmonic oscillator. So prior to that, we have like the general quantum mechanics formalism.
Okay.
Then
All the Schrödinger picture, Heisenberg
Heisenberg
picture,
pictures,
all of them.
right, and the operator and all these kind of
Operator
things.
things. Okay.
And then in the 7th week, we have the hydrogen atoms and like the angular momentum.
Wave function.
Right, hydrogen atom. And prior to that, we have the angular momentum algebra and the property. So these are the things that are covered.
That has been done.
Right.
Course. Yeah, any questions you have, you should just start asking us. Then we can start answering your questions.
Yeah.
How many have registered for this course?
I think it's around 800 or so. I don't know the exact number, but
Around that.
yeah, around 1,000.
You have also emailed that
right,
there is going to be a live
Yes,
session,
right.
right?
Yeah,
I'm
because
surprised that very few people are joining. So nowadays for the live session,
right.
they don't want the live session. You can also ask next time if they don't want a live session, we will not conduct because
No, like prior to that, it was also informed, right? And then we have announcement for the postponement of this.
no, that is fine.
Right,
But
right.
even
But they know like where
No.
the live session is and all this thing.
no, if they don't want if they don't want the live session,
Okay.
if they just want to ask only questions on the portal,
Mhm.
then also is fine. The live session is mainly for them to ask any, one-to-one questions if they want to ask.
Right, right.
We are available to answer. But if no one, very few students are going to join here, then it's easier for them to come to the portal and ask their
Right.
questions. We'll wait for another 10-15 minutes. If there are no more chat questions,
Right.
we may have to sign out.
Right. Because most of the questions on the portal has been answered.
Yeah, that's right.
Right,
That's
right.
what I'm saying.
Right.
They are
Yeah, but the
benefiting
purpose
from
of
that.
the live session is the different. So I
Yeah.
think you're seeing it.
And also, if they don't find this time slot convenient, they should tell us. Then we can fix a time slot where everybody will be sufficiently free to take up this active participation.
No,
right?
I think in the Google form, so
Yeah.
there's an option like which if we
Which time
propose,
slot?
yeah,
Yeah.
which time slot they will be available in this kind of thing.
Okay, and they said this time
Yes,
slot
yes,
is
yes.
convenient.
Yes.
Excellent.
Right.
I see one participant, but probably it is us or
Maybe I think so. But so this is for the Zoom, no? This is
Yeah.
for the Zoom. So for live, like the participant, we don't know from here because even if it is not, we don't know from where we will get.
number of persons.
Right.
Two watching now started streaming 4 minutes.
Okay, so maybe there are.
Hello. You have any questions? Start typing on the chat. Then we'll be able to respond by working out some of the steps for you.
Right.
Okay. How many are joined? 2. Huh? But we don't see any of them typing any chats. So 3, 4 are joined, right? That doesn't include us, I guess. No? So you can type there. Why don't you type? Can you type?
Okay, there's
Yeah, there is.
there's a question here.
Yes.
Can you
Yeah. So can you clarify regarding orthogonal polynomials for hydrogen atom wave functions? Okay. See, first of all, wave function, when we write, right? Wave function has to be some kind of a known special function. Okay. And why do we choose special functions or known special functions? See, polynomials, let's take one dimension. You can write monomials like 1, x squared, x cubed, and so on, right? This also probably I've explained in your.
You can just do the share. Here is the pointer.
Here also?
Yes, sir. You can share. And then the line.
Yes. So we go 1, x squared, and so on. You can write all possible monomials as a basis function. This is also allowed. It satisfies all the properties that any arbitrary function of x can be written as linear combination of, right, some coefficient times x to the power of n. But why don't we choose that as the basis function? The reason is that ideally, when you write a position vector, right, you choose I hat basis and j hat basis, one along x-axis and y-axis, with the condition that I dot j is 0, and I cap dot I cap is 1, and j cap dot j cap is 1, right? This is what you choose as a basis. You choose 2 orthogonal x coordinate and y coordinate are orthogonal. By that you mean that the dot product of the unit vectors along that direction is 0. This I cannot do here in the functional space if I just choose monomials. Instead, if I put a condition that x, okay, is less than 1, okay, mod x, let's say, is less than 1 or less than or equal to 1, then I can work instead of 1x squared, I could work with 1x 3x squared minus 1 by 2 dot dot dot. I call this as Legendre polynomial P1 of x, P2 of x, and so on. Okay. Advantage with this is that when you do an integration of dx from -1 to +1, Pn of x, Pm of x, this will be having this orthonormal property. Okay. This is the advantage. And we would like, just like you had I hat and j hat, in the functional space, you need to do the dot product should be like an integral over the domain with this, and then that should satisfy this orthogonal property. And this is useful because when I write the same arbitrary function f of x, I could write it with some other coefficient, Pn of x, okay, where this Pn of x are orthogonal to each other by this definition, okay? And this is useful. This is for the domain where x is lying between -1 and +1. And if you remember in in the harmonic oscillator, x is like cos theta, and cos theta value runs between -1 and +1. But if you go to hydrogen atom, the x can be promoted to your radial coordinate r, And radial coordinate range is from 0 to infinity, right? There, the corresponding polynomial form is not going to be Legendre, but it will be Laguerre functions for the radial. Okay, so this is the way you have to start looking at what, so sorry, the angular part theta which you do here is for the Legendre, that is also for the angular part of the hydrogen atom. If you did harmonic oscillator, the next runs from minus infinity to plus infinity, there you have to use Hermite column, right? Hermite. So you should correct me, I'm just mechanically saying. Yes, so these are required when you do the angular theta part. And Laguerre functions is required because the domain of the variable radial coordinate is from 0 to infinity. There it will become Laguerre coordinate. Yeah. So they are convenient because you can write f. So I will call x as cos theta just for convenience. Then you understand. So the angular part can be done this way. And similarly, I can write g of r as some Cn and then a Laguerre function which is dependent on r. Okay, and this R domain is from 0 to infinity. And similar equation which I wrote, I can write 0 to infinity dr, and then I can put the Laguerre function to satisfy this orthogonal problem. Does that answer your question? I don't know what is your name, but I see that as Dinakar maybe, I don't. Yeah, is that answering your question? So that's why you start seeing these orthogonal special functions which dictates the definition of the energy eigenfunctions of the hydrogen atom. Okay. Yes. Yes. So, any other question you have? So just correct, I said for harmonic oscillator it is Legendre, it's not Hermite polynomial. Yes. So please correct it. Legendre comes for the angular part of the hydrogen atom and Laguerre comes for the radial part of the hydrogen atom. Yeah. Any other question anyone else has? Any other doubts you have in the lecture where you need some more clarification? Please feel free to, please feel free to ask us. We are here to clarify. I've not prepared any lecture. Depending on what you ask, I can answer for you. Yeah. These functions are in the first principles, but I find it difficult to understand it. I can't find its prerequisites. Okay, so special functions, just like you learn integration, differentiation, right? Special functions, you don't need to memorize. It's available, okay? So it's useful because sometimes when you have various symmetries, like if you have a spherical symmetry, sometimes we use Bessel functions. The special functions are solutions to these second order differential equations. Some of these things are available in the literature. You don't need to memorize, but it helps you to write it as orthogonal combinations, but if you just write some arbitrary function of r as 1 r squared, then the computations can get very tedious. Okay, so you don't need to really memorize or understand, but there is an equivalent basis. You can work with monomial basis, or you can work with some linear combinations of these monomials, which are orthogonal to each other, orthonormal, I would say. And they are really useful and very powerful in doing your computation.
Because Schrodinger equation itself is second order.
That's right.
So, and our ultimate aim is to find out the solutions of the Schrodinger equation.
Yes, yes,
So these like special functions are the
yes.
like tools to find out the solution
Yes,
for
some of
special
them
cases.
are available. So
Right,
in the literature, we are not trying to derive.
Right.
We just mapping this differential equation resembles the mathematician's special function equation, differential equations. So in that sense, we don't need to, we're not deriving that special functions are required in quantum mechanics, but this differential equation exactly resembles the differential equations in mathematics literature where the solutions are those special functions. That's the right way to understand. Is that clear, Dinakar? So no prerequisite. We just say that these differential equations are known in the literature. Okay.
Otherwise, life will be very difficult to find out the solution for this kind of system.
In fact, for any arbitrary potential, we don't see any special functions as solutions, right? Like you can ask for other kinds of potentials. Okay, there we don't know. You can numerically solve it. Now that with this AI, machine learning, deep learning, maybe it's possible to solve order by order, finding solutions. But these are exact solutions because for harmonic oscillator, the equation exactly resembles the Hermite polynomial differential equations and so on. But that's not true for arbitrary potential. You can have arbitrary potentials, potential energies. For that, we don't have such special functions as solutions. I've not really spelled it out in the lecture. The usual mod X potential, if you take, I probably said if you do a Fourier transform, it will look like solving it in the momentum space, the wave function. The actual solution is Airy functions. Okay, that's also a special function.
Right. Yeah.
Right? Yeah, so some of these are some potentials like mod X, which is simple looking. There also the solutions are special functions which are like Airy functions. And there are many polynomial potentials for which we don't know the exact closed form wave functions or energy eigenvalues. Sometimes we do it order by order. If you do the advanced level quantum mechanics course, there is something called perturbation theory, approximation methods like variational methods, which is WKB also, variational methods, WKB. So many approximation methods by which we try to solve, corrections. And they're not exact. Order by order, we do a calculation. Okay, so it's not always possible that we know what is the special function for the second order differential equation for arbitrary potential energy. These simple examples are toy examples for which it is known, and we teach in this course for clarity. So there are many challenging potentials for which we don't have a solution. Sometimes they map one different looking to another one by some coordinate transformation, sometimes by, there's a possibility of finding a solution. But these are really, students who are interested can invest time and find some elegant way of finding solutions. So there are many students who have joined, but nobody is putting on chat. Maybe they're just listening to the answers. Okay, so can you tell about matrix and bracket formalism for problem solving? Okay, first of all, the matrix representation.
Yes.
See, there are two ways in which one could solve. If you are working with finite number of states, okay? By that, what I mean is, if you remember hydrogen atom, and if I say that we are in the p orbital, not really getting on to more details, but if it is p orbital, then you know what are the quantum numbers. And I'm not really worried about, let me take n equal to 2, which is the principal quantum number, which you have learned in chemistry or in your school 12th standard kind of course. And p orbital, if I say, this means that the azimuthal quantum number is 1, right? And the magnetic quantum number can take 3 possibilities, right? Can be -1, 0, +1. So formally, I can write in the bracket formulation that I can write I will not worry about this n equal to 2, but I will write L comma M as the state. Okay. And then this state means L is 1, L equal to 1, let's say. Then this means that it is a 3-dimensional linear vector space. Okay. So there are 3 basis states: L equal to 1, M equal to +1, L equal to 1, M equal to -1, L equal to 1, M equal to 0. Now, when I want to put operators acting on this state, okay, these operators, I can write it as, you can write operators, I have discussed this in lectures, that it will be some summation over, M comma M1 or M1 M2. You can have a C M1 M2, L M1, L M2. I'm just using L as a variable which is 1 here, right?
Right.
That's one way of writing this operator form. But I can also write these coefficients as in a matrix form. So I can write it as a matrix with M1 going this way as +1, 0, -1, M2 going this way as +1, 0, -1. And each of these elements are C11, C10, C1 -1, and so on. Okay. So this is an equivalent way of writing the Dirac bracket outer product of any operator. And you can also formally write CM1, M2 to be L equal to 1, M1 with the operator, L equal to 1, M2, right?
Right.
So these I've taught in the class that these are equivalent ways of playing around a formal structure with a Ket notation, Bra notation for the dual vectors, dual space vectors, and writing the operators and outer product, finding the matrix elements of those operators by trying to write it as, the inner product with the state L M1 with operator in L M2, and formally you can write C as a 3x3 matrix for L equal to 1. Does that answer your question? And once, if you're very familiar with matrix formation, matrix way of doing things, you can, if I give 2 operators O1 and O2, write the corresponding matrix form of it, multiply and do it. Or you can apply O1 operator first, then O2 operator second. You can do it in this elegant Dirac bracket notation. And both are equivalent. And I'm trying to stress this in this course because this elegant notation of bracket formulation will help you to go to advanced courses. Of course, you can work with these matrices, but you should know how to toggle between one and the other so that you understand both the notations. Is that okay? And once you understand, all your problem solving can be done here or here for finite dimensional linear vector space. But whatever I'm writing here can be extended to infinite dimension by putting an integration and so on. So that way the bracket, Dirac bracket, outer product for operators, inner product of states, all those things. I have invested a lot of time in explaining it in the lectures, and it will be good for you to get a clarity, and all the problem solving are also in one-to-one on-to with whatever I've been teaching, right?
Right.
Yes. Does that clarify your question about matrix and bracket formulation for problem solving? Now you should go back and look at some of the problems and try to solve it again.
Anybody else have any questions, like they can just put on the chat box so that we can discuss.
Are there any specific students who keep asking a lot of questions in your portal? Any names you can recall?
There are some questions who repeatedly ask, but
Okay. You
some,
can't
but
recall.
I don't exactly know
Remember
the
the
name.
names.
Yes.
Don't feel shy. The aim of this live session is to come at least once in a month or once in 6 weeks to help you out. If you have any specific questions, anything. By the way, registration for exams and all you should do, right? There is a deadline. When is the
No,
deadline?
deadline is passed. I think there's a pre-deadline, and then we have extended deadline for registration, like
For
if,
exams?
yeah, for exams also, like if some.
Okay, so that's
Oh,
over.
right, that's over, I think. Yes, yeah.
Yes. Also, you can keep as a guideline couple of books which I've recommended, and it helps. And it's a very important course given the topical area of quantum computation and other quantum information. Some of these things are going to rule in the next couple of decades.
Right.
And learning the tools of quantum mechanics is really essential. Okay. Some of them are very abstract, not that we understand. Our intuition really doesn't give clarity, but logical steps and confirmation with experiments kind of reinforces that world is very microscopic world is very counterintuitive.
Right.
And many more efficient algorithms, fast computation are all going to be dependent on these superposition principles, error minimization, a lot of things. Some of these things really hinges on quantum mechanics, learning these first level course on quantum mechanics, and then getting on to advanced courses will actually help in appreciating what is going on in the quantum computing world if anybody's interested. Yeah, if there are no further questions, I may have to sign out in another 5 to 10 minutes. But if you have any other questions, yeah, good. Symmetrization postulate, madam. What is symmetrization postulate? Okay, so in what context did I talk about this collection of two identical particles? I was talking about symmetric and antisymmetric.
Yes, yeah,
Yes.
that's the one.
Okay, so let me try and first of all, you go and look at any specific, pattern seen in a specific tree or a plant. The leaves in a plant will have some kind of a pattern. Okay, each leaf will be identical, and if the leaves are coming like this, another place it will not come like this. It will come the same symmetric way. Okay. So that's one thing which is nature follows some kind of a symmetry pattern, and it's very beautiful, right? You can see a lot of fruits also, the way they stack in a pomegranate, the way things are in the shape of orange comes in a round fashion, and bananas are in a different shape. Each plant, each fruit, each leaf is characteristic, and there is some kind of a symmetric pattern also. Okay. So this is something which nature has. And typically when there is a symmetry, sometimes you look at a mathematical equation. Let's take harmonic oscillator. You know that the potential energy for the harmonic oscillator is half kx squared. Staring at it, you see x if I change to minus x. Okay. The potential energy remains the same, which means we indirectly know the wave function psi of x and psi of minus x have to be related up to some kind of a phase factor or plus or minus sign. So the symmetry plays a very important role. Okay. So in that sense, symmetry of two identical particles. If you take two identical particles, okay, can you see me? If you take two identical particles, you can exchange. Okay, if I didn't show you that I exchanged, and I asked you whether the configuration, you close your eyes and open your eyes, both are identical particles. You will say the state looks the same, but actually I've done an operation. So this operation, somewhere it has to be coded, and we need to make sure these two particles are electrons, let's say. Electrons should obey, two electrons should obey Pauli's exclusion principle, right?
Right.
So that's why when you start writing the nomenclature for helium atom with two electrons, you write it as 1s2. The way you write 1s2 means you say first electron is also put in the S shell, and the second electron also you put it in the same S shell, but you make sure that the first electron is up, second electron is down. What is the reason? Pauli's exclusion principle tells me that the quantum numbers of the first electron, all the four quantum numbers. So n equal to 1, L equal to 0, M equal to 0, and I'm going to put spin as up. So here again n equal to 1, L equal to 0, M equal to 0, but in the fourth one, I have to choose it to different. Otherwise, Pauli's exclusion principle will be violated, right? I'm sure all of you know this. So this is where you use two identical particles when I exchange. Both the particles should not have the same set of four quantum numbers if it is electron. But if it was, let's take pion particle or a boson particle or a photon, okay? They are bosonic in nature. If I exchange, you don't need to worry about Pauli's exclusion principle for bosons. Okay, so that is the one which we use when we write the wave function for a system of two particles. Two particles are bosonic. All the four quantum numbers for both the particles can be same. Okay, I don't need to put the second particle down if it is bosonic. I could have put it like this. So anyone is interested should go and look at this Bose-Einstein condensate. If I put n number of bosons, all of them can be in the ground state. If I put n number of electrons, Okay. Only 2 electrons in the first 1s. Then I have to go to 2s, 2 electrons. And then p, how many I can put? In 2, I can put, there are, p has 3 possibilities, and each of these possibilities I can put 2, 2, 2, 6, and so on.
Right.
So then that final end level will tell you what is the Fermi level. Okay. So these are some things which you should go and explore and understand. So identical bosons, all of them can be in the ground state. It is symmetric. The wave function does not look different when you exchange them. But identical electrons, if I exchange, it will pick up a negative sign. Okay. So these are dictated by Pauli's exclusion principle. The negative sign, the reason is if both are identical, it means that identical equal to minus identical means wave function cannot exist. It is 0. Okay. So that is why symmetrization is important for identical particles. And how symmetry matters for particle physics, this also you all know. I'll come back to your other question about what is the first excited wave function of 2 fermions in 1D box. I'll come back to that. Before that, let me try and say in particle physics. So first of all, simple things, observations dictates us to create theory. Okay. Proton and neutron. Okay, if you ask what is the mass, all of you know mass is almost the same, right?
Right.
Right. If I write 1.6 into 10 to the power of minus 27 kg, it can qualify for both of them. There could be
Right.
the next decimal place where there is a correction,
Exactly.
right?
Right.
So why is this? Proton and neutron have the same mass. Made the particle physicists to come up with some kind of a logical symmetry argument called isospin symmetry. Okay. It's not very different from your rotational symmetry, but this is just like your spin symmetry is an internal space. Isospin symmetry is in the another internal. So this is the one which answers why the mass of proton and neutron is almost same. Then you'll ask, actually it is not same, right? There is some difference.
Right.
Right? And how do I see the difference? Proton is positively charged. This is neutral, right? So if I turn on an electromagnetic field on a neutral particle, nothing happens.
Right.
But if I turn on an electromagnetic field, proton will feel some kind of a interaction. Agreed? So that interaction can bring in the change in the mass. So as long as you are in a vacuum with no electromagnetic interaction, you can be in total bliss. Proton and neutron are almost the same mass. You cannot see the difference. It's like Zeeman effect, right? If you turn on a magnetic field, the p shell electron, if this magnetic quantum number is m equal to +1 or -1, they will split. Right? Because of this mu dot B term.
Right.
Otherwise, it will not split.
Exactly.
So if you are not turning on magnetic field, all the levels will be degenerate. Similarly, proton and neutron will have the same mass as long as you're in a vacuum with no electromagnetic interaction. So this is where particle physics symmetry gets one by one added, and we start bringing in a bigger symmetry, which leads to standard model, and now we go beyond standard model as well. Okay, so that answers I think Harshul is asking another question, Dinakar's question. Is that okay? Harshul, I'll explain what you're asking. What is the first excited wave functions of 2 fermions in 1D box? So you tell me I should not violate Pauli's exclusion principle. Okay. And I should write a wave function of first electron and second electron. Okay. And I will write this as phi of first electron, phi of second electron. Okay. But I need to make sure that, so this one, let me call this as the N1 and N2. I could say that the second electron is now having quantum number 1. and first electron has quantum number 2 or quantum state. Okay. Is that clear? But now I need to put a minus sign to make sure that if N1 and N2 are equal, such a state should not exist. Okay. So this is in general required, and I will put a normalization as 1 over root 2. Okay. Where phi N1 is your particle in a box. For the particle 1, so I will write it as root of 2 by L sine n pi x x1. Let me put for particle 1 as x1 as the coordinate divided by L. For particle 2, I'll put x2 as the coordinate. So this is for the most general wave function where one particle is in the quantum number, quantum state N1 and another particle is in N1. Now we are asking what is the first excited state of two fermions in 1D box. So you need to make sure that the total energy goes, lowest energy is going to be N1 squared plus N2 squared, right, times E naught. And N1 and N2 are 1 and 1. Both cannot be in 1 and 1 for fermion. Okay? Agreed? So the ground state will be N1 equal to 1 and N2 equal to 2. That is important, right? You can't have it to be ground state with both N1 and if you include spin, you can put both of them in the ground state, but then you have to multiply by a spin quantum wave function. If I say ignore the spin, or if I say both the spins are same, then N1 equal to 1 and N2 equal to 1 is not allowed. Correct? So ground state itself will be, if you suppress the spin quantum number or assume both the spin quantum numbers are same, then N1 equal to 1 and N2 equal to 2 is the ground state. Then first excited state. Okay. So first excited state will be, you need to choose N1 equal to 1 and N2 equal to 3. Is that going to be a intermediate energy or N1 equal to, which one will be true? N1 equal to 1 and N2 equal to 3. What is the energy? And N1 equal to 2 and N2 equal to 3. Which one is bigger? So this is probably 9 plus 1 is 10.
Right.
This one will be 4 plus 9 is 13. So this is second excited state. This will be the first excited state. Does that answer your question, Harshu? So this will be your 9 plus 1 is 10. It is 4 plus 9 is 13. So this will be second excited. This will be first excited. That's what I would do when I have to stack, assuming that both the electrons have the same spin quantum.
Right.
If you allow both the electrons having different quantum numbers, my ground state will be N1 equal to 1 and N2 equal to 1. And then you have to do the next exercise, which is the first excited state is N1 equal to 1 and N2 equal to 2. Will be the first excited state. We both have one is up and another one is down. Then I can choose that. Does that answer? Here I have assumed that the spin quantum number is symmetric, so I have to make the spatial quantum number to be antisymmetric. Does that answer your question, Harshul? Anything else you have? Very good. If you ask certain questions, then I'm also able to clarify once you ask these questions. In this course, mostly when we did hydrogen atom, harmonic oscillator and all, we did not really put the spin quantum number, but technically you can multiply the spin piece. In particle physics, we also multiply the isospin piece and so on. Okay. So we need to take care of all the internal spaces and what is the symmetry involved and so. Okay. Right now, you don't need to worry. We're just doing initially the spatial part of your wave function. And then Stern-Gerlach experiment, the spin part also, we put it by hand. But spin, instead of putting it by hand, can we get it formally from a theory? Yes. But in your course, we have taken kinetic energy operator to be p squared over 2m. You all know p squared over 2m kinetic energy is only for non-relativistic particle. If you take relativistic particle, you have to take Einstein's total energy and subtract the rest mass energy. Then only that is the kinetic energy. If you start doing that, then it becomes relativistic quantum mechanics. We are not doing relativistic quantum mechanics in this course. For many atomic physics problems and experiments, doing non-relativistic quantum mechanics is good enough. You can reproduce the results, experimental results. But ideally, spin quantum number is required. And to understand spin quantum number, we can put by hand. But if we can get it from the theory, it will be nice. And then relativistic quantum mechanics helps us to get the spin quantum number in a natural way. That's where the Dirac equation comes in for the electron. And that's not part of this course. Okay? Yeah.
Right.
I think we are almost some 5-6 minutes left. If you have any 1 or 2 quick questions, you can you can say spin is seen only in a relativistic quantum mechanics setting. Yes. Fine. So here we put spin by hand. We do write mu dot b, right?
Right.
S dot b
Right.
when we write.
Right.
We give you a problem with saying that the system is subjected to a Hamiltonian, which involves S dot b or S1 dot S2 and so on, right?
Right.
But ideally, can I understand that term in the Hamiltonian coming naturally? Those things can happen if you do take the kinetic energy operator as a relativistic operator and not p squared over 2m. Okay? No, that's true. Spin has no classical analog. And the spin quantum number, if you want to explain, you have to be in relativistic quantum mechanics. Yes. But for all practical purpose in this course, even though you're doing non-relativistic quantum mechanics, we are putting by hand the spin quantum number, which is okay. See, many times you can also write an empirical term. And then we are explaining what you see in the Stern-Gerlach experiment and other anomalous magnetic moment and so on. So in some sense, Zeeman effect, right? Like many things, many of these things, you can explain the corrections and many problems you will do where we do give you the Hamiltonian by hand. Okay. So in that sense, spin quantum number, if you really want to understand, see, we started with L. L is understandable in hydrogen atom. But I add L plus S and I say S behaves like L. All those things are given as postulates in this non-relativistic particle. Right. If you want to understand L plus S, what exactly it is, if you go to Dirac equation, you start seeing some sigma, right. And then you start seeing rotational symmetry is not dl by dt equal to 0, but then there is total angular momentum and all we understand. Here, we are trying to give you by hand. Whatever happens for L, it will happen for S. That's why we constructed the Pauli matrices, which satisfies the same property. Okay, so I think we will see you. This question is away from quantum mechanics. What is actually strangeness in particle physics? See, the thing is, when you take a particle, each particle has charge, mass, okay? And then we start inventing more and more quantum numbers by looking at a process. A plus B going to C plus D is a process. Is this allowed or it is forbidden? Okay. Experimentalist tells us we don't see this particular particle plus another particle going to some products. How do we understand? Then we say, okay, we'll assign baryon quantum for every particle. We'll assign strangeness quantum. So we start doing it and say the strangeness, just like you have charge of initial set of objects, A plus B, matching with the charge of the products, right? You do the charge conservation, angular momentum conservation, momentum conservation, linear momentum conservation, energy conservation. For any process, A plus B going to C plus D, you do all these things. Now we start inventing. We'll invent Perron quantum number. We invent strangeness quantum number, mainly to make matching with known processes in the lab, why it is allowed, why it is not, why it is forbidden. Okay. So this is where strangeness quantum number is also introduced.
Right.
Okay. So more things you can read from a book by Griffiths on particle physics, right?
Right.
Yeah. They have this list where they show some processes cannot be explained if I don't introduce strangeness quantum number. So, okay. So let me stop here. I think we are running out of time. We'll see you next time. See more people next time with more questions to start immediately as soon as we start the live session so that we don't run out of time because they have another live session after this. Bye-bye. See you. Bye. Anita. Praveen.